So our next speaker is Laurent Chiablé. He's a research geophysicist at Sandia National Laboratories, looking at geophysical acoustics, especially infrasound monitoring, related to a variety of natural phenomena such as earthquakes, volcanic activity, but also anthropogenic ones such as explosions. The floor is yours.
Hello. Hello, everyone. My name is Laurent Chiablé, and I am very honored to present today in this very beautiful and historic city. So I am coming from Sandia National Labs in Albuquerque, New Mexico. And today I'm going to be discussing my research on behalf of my colleagues regarding the relationship between the seasonality of sea ice extent and the microbarometer as recorded at high latitude international monitoring stations. So infrasound is atmospheric pressure fluctuations below the nominal hearing frequency, so generally between 0.01 and 20 hertz. And the global infrasound environment is comprised of natural sources such as avalanches and earthquakes, but also anthropogenic sources, including space vehicles, and of course, most important to this organization, explosions. And all of these sources are relatively confined in both source location and duration, except for what is perhaps the least dramatic, but perhaps the most problematic of them. Thanks. Which is the microbaromes, which is caused by the constant movement of ocean on the Earth's surface. Next. I'll try. And today I'm going to be discussing how environmental factors such as sea ice coverage in the hemispheres and storminess can in turn affect the microbarometer, which can in turn affect our detection capacity. So microbaromes are the acoustic consequence of the same process that creates the microseisms, which are generally more widely understood. But it is noise created by interference of opposing wave trains with similar frequency on the ocean surface. So here you have a wave moving to the left and a wave moving to the right, and the product wave creates pressure tractions on the ocean floor, which travel through the solid Earth as microseisms, and that's generally what people are more familiar with. But the product wave can also create pressure fluctuations at the water-air interface, which then travels through the atmosphere and is recorded as microbaromes. So these are the dominant acoustic and seismic noise features on the Earth, respectively. And they are ubiquitously observed, and they are persistent through time, and share a similar frequency band due to their common origin mechanism. And lastly, because they are both affected by environmental conditions, they are seasonal and generally greatest in winter when there are more frequent and larger storms. So here we have a probabilistic power spectral density for 1 year of hourly recordings at an IMS infrasound station. And you can see the dominant feature here is at approximately 0.2 hertz, and that is indeed the microbarometer, which is defined as lying between 0.1 and 0.5 hertz. And as you can see, it lies smack dab in the middle of the IMS monitoring band determined by treaty negotiations of 0.2 to 4 hertz. And as such, the microbarometer is widely understood to already be a substantial obstacle to the IMS infrasound goals. And the problem, the crux of the matter that motivates our research is that variation in microbarometer amplitudes could in turn affect our monitoring, and that is the issue that motivates the two research questions that we're going to discuss. So the first one is, does the microbarum exhibit any secular trend, which is just trend over time? And the reason why this is a particularly salient question is because the microbarum, which I discussed earlier, has been shown to be trending upwards at approximately 1/4 to 1/3% per year, and has actually been shown to have accelerated since the beginning of this century. And that trend is attributed to increasingly energetic noise or ocean conditions. And given that the microbarum and the microcysum have similar origin, we suspect that similar effect may be had on the microbarum. And secondly, we are curious about the relationship between sea ice extent and microbarum amplitude. And the reason why this question is important is because strong sea ice has been shown to inhibit the growth and passage of waves, thereby diminishing both the microcysum and the microbarum. And there is an enormous degree of variation in sea ice extent over the course of the year in both the northern and southern hemispheres, to the tune of about 1 million square kilometers. And of course, sea ice in the hemispheres is varying not just intra-annually, but over time, with a consistent decline in coverage of 1/2 to 3/4% per year over the last 10 years in the northern and southern hemisphere. So to investigate these relationships, we collected data from 6 of the highest latitude infrasound stations, and we collected 10 years of data beginning in 2014 and through the end of 2024 from 1 element per station array. So here, I-53 US in Fairbanks, Alaska, we took data from the 1 element shown in red. And of the 6 sites that we analyzed, you can see that the coverage over this period is quite good, exceeding 93% in all 6 sites. So regarding the secular trend, we calculated what I call an integrated microbarum value between 0.2 and 2 hertz for every hour in the 10-year duration. And then we calculated the linear trend within each of these. So firstly, each of them has a seasonal variation, which is consistent with previous work and expected, as we discussed earlier. But regarding the secular trend, we do not find a consistent trend amongst all 6 of these sites. We find 3 positive trends, 2 negative, and 1 near 0. We do find, when we compare with trends taken from nearby seismic sites, we find agreement, so both positive at 2 of the sites and disagreement at the 3rd. We believe that there is much more to be learned from these relationships, however, and for example, you'll notice that I-55 in the lowest row, that's a site in Antarctica, has a particularly strong trend in both the microbarum and the microcysum, and we hope to learn more about that in subsequent study. So regarding the relationship between the ice extent and the microbarum amplitude, we have these 2 time series, and we wanted to analyze the phase relationship between them. So we collapsed this data per calendar date to data per numerical day of year, which is shown in this plot. On the x-axis, you have the numerical day of year between 0 and 366. On the left y-axis, you have sea ice extent in millions of square kilometers per year, and that is shown in the black and gray lines. And on the right y-axis, you have the integrated microbarum value shown in red, with each thin line corresponding to one of the years, and the bold red line corresponding to the median over the course of time. So the most salient, important observation of these 2 approximate sinusoids is that they are phase offset, such that the microbarum line precedes the sea ice condition, in this case by 2 to 3 months. Now, we did this analysis for each of the 6 sites. Here we have the 4 northern hemisphere stations on the left and the 2 southern hemisphere stations on the right. And as you will see, the northern hemisphere stations are generally better behaved than the southern. And there's a great deal of variation both within sites and across sites. But the broad observation pertinent to this discussion is that at all 6 of these sites, we found an approximate 2 to 4 month phase difference between the integrated microbarum and the sea ice condition. So we take this as evidence that sea ice is not the primary driver of microbarum amplitude. And again, there's much more to be learned from these from this data, but that is the primary conclusion we are taking for the purpose of this discussion. So this work is largely preliminary, and we have a great deal more work that we hope to do. However, for the our first question, we find it inconclusive so far. There is not a primary relationship consistent to all the sites that we analyzed. But regarding our second question, we do believe this is an important finding, that sea ice is not the dominant driver of microbarum amplitude, and instead we believe that microbarum amplitude is being driven more so by the storminess conditions over the hemispheres, such that the northern hemisphere is stormier in the northern hemisphere winter and vice versa for the southern hemisphere. We hope to continue this work. We want to analyze more IMS infrasound stations. So far we have analyzed 6 stations, 10 years each, and that is admittedly a relatively small subset of the available data. So we would like to analyze data from all 53 IMS infrasound stations, and we would also like to analyze the full period of record available for each of those stations. The earliest IMS infrasound records go back to 2001, which 24 years is a pretty decent record. And lastly, we would like to consider narrower and different passbands. So as I discussed, my integrated microbarum value was between 0.2 and 2 hertz, which is not the microbarum per se. We want to analyze the strict definition of the microbarum, 0.1 to 0.5 hertz. But we're also interested in other passbands to understand other sources of noise. So with that, I thank you very much, and I am happy to take any questions.
Thank you very much. Is a question here? Just getting the mic.
Yes, thank you. And on your last point, I think that's very important, because if you start at 0.2, you cut right through the microbarum peak. So when we study microbarums, we would even do it between 0.1 and 0.3, just to make sure that you purely focus on the microbarum band. Going much beyond 0.5, you may start to include surf, breaking waves on the coast, especially at I-53, for example, which you have used. They are very prominent. So I would be very narrow in your band. But that's just a remark. A question: what made you decide to use one array element rather than an array average value or some kind of other metric, because you become quite sensitive to the functioning of that one specific element then?
Yeah, that is true. It is strictly been a case of data management and data analysis so far. It would be great to incorporate the data from all of the elements at every site and even do array processing, but that just hasn't been in the scope of our work so far. Yeah, thank you.
In the interest of time, I think we should probably move on. So, Lauren, once again, thank you very much.
Thank you.